Hey everyone, today we're going to be talking about Bernoulli's equation and volume flow rate, two things that you will see quite a bit this week in class. And also, we've seen every single year on the AP Physics 2 test, so you know they're important. So let's start with Bernoulli's equation. If I have my stuff together, I will snip a picture of it from the equation sheet and show that on the screen now. Cool, so make sure you know where that is, know where to find it. I'll write it down here too. It's cool. I like it because it's one of the most complicated looking equations we see this year. So P1 plus rho G H1 plus 1 half rho V1 squared equals P2 plus rho G H2 plus 1 half rho V2 squared. You look smart just by writing that down, which is pretty darn cool. Today I want to talk about a couple situations where this equation can come in handy if you know some little derivation tricks. So those situations often involve a large container of some kind. Usually that's like a big bucket of water. It could be like a drinks cooler or something bigger like a water tower or something like that that has a hole in the bottom. So it either has a leak and it's dripping out, or sometimes there's like a little hole in the side here. And if you imagine we have this big cooler full of water, if we have a little hole, maybe we've got tape over it, and then we rip the tape off, you're going to get a little water shooting out of the side. So using some derivation tricks, we can even say it's up on like a little stand or something here above the ground. I don't know, 3D legs. Using some derivation tricks, you can calculate exactly where this water is going to hit the ground, and using some projectiles and things like that. And to get there, Bernoulli's equation is going to be our guide. So starting with Bernoulli's equation, there are some assumptions that we can make about point 1 and point 2. So let's say point 1 is right at the top of the water. So we've got a water cooler here, and it is, let's just say it's full all the way to the brim. And we could say point 2 is down in here, right when the water leaves from the side. So it's leaving as a horizontal projectile. And there are some assumptions we can make. First, if this is an open container, and we can assume that there's no like lid with air pressure pushing down on it, the pressure, external pressure to the side here, P1, is going to be equal to atmospheric pressure, because what's pushing down on it? Well, the air. And then when the water leaves from the leak over here, the pressure pushing out is equal to air pressure because it's just exposed to the air. There's not greater pressure. It keeps the same size as the hole. So when it leaks out, P1 and P2 are actually going to be equal because they're both equal to atmospheric pressure. It's exposed to the air here, and it's not expanding or contracting or anything like that. And it is equal to atmospheric pressure. So we can eliminate both of those terms from the equation because they're equal to each other, so they would cancel. Next, we can choose, if we're comparing points 2 and point 1, we can make our height equal to 0 at point 2. We can just choose this as our 0 point. So you could list that as a 0 if you want, if that helps. And then we can measure the top of our cooler here. And let's just say it's a whatever, H. You can call that whatever you want. But if this height is equal to 0, this entire term is going to be 0 because rho times G times 0 would be 0. V2, we can't say anything about that yet because it is does have a velocity. That's what we're going to solve for, or we'll see that'll come out in a minute. And then there's an assumption we can make over here that we will actually clean up this side of the equation as well. So that's going to be with V1. If you imagine a really, really large container with a really, really small leak, it's true that as water leaks out, the total volume is decreasing because it's going out through the hole, and the water level at the top is going down, which means there is a velocity up here. However, we're going to assume that the velocity at point 1 is so small that we can just exclude it from the equation and not have to worry about it. And we're going to make that assumption because we have a really large container. There is a velocity, but we're going to say that with a small leak, the water level is going down so slowly that this velocity term isn't going to have a big impact. So it's going to be much smaller than this velocity term over here, and it's going to be smaller compared to this gravitational potential energy term. So we can just assume that this term is really, really, really close to zero and just eliminate it, which makes our life a lot easier if we make that assumption. So we're left with rho GH1 equals 1/2 rho V2 squared. Rho is just the density, and it's the same fluid, so we can cancel those. We're going to assume that water has constant density, which we'll do for all of our problems this year. In some really weird real-world situations, water can actually be compressed, but you have to have really, really high pressures to do that. So we'll assume that the density is constant. So then we have G times H1 equals 1/2 V2 squared. And then our H1, we can plug in H, which is just the distance from the leak here up to the top. So G times H equals 1/2 V2 squared. And now let's go ahead and solve this for V2 so we can know what the velocity is of the water coming out. So multiply by 2. So 2GH equals V2 squared. And then we can take a square root to say V2 would be the square root of 2GH. So that tells us what the velocity of the water is here. If you wanted to find this point on the ground where the water is going to hit, from that point, the water behaves exactly like a horizontal projectile. So you know the initial velocity because you can measure H, you know what G is. So all you have to do is treat it like a horizontal projectile, split up your X and your Y. Maybe you'll make a table for that. But any of those will turn into a projectile problem from here. So I'm not going to show you that part. We reviewed projectiles a couple weeks ago, so you should be pretty comfortable with that. The last thing I'll point out before we talk about volume flow rate is that this is true if the leak is on the side, the leak is in the bottom of the container, the leak is higher up, lower down. As long as you're measuring the height difference between the top surface of the water and wherever the leak is, this equation will tell you the velocity. If it's in the side, you can assume that it's going to be a horizontal projectile. If it is in the bottom of the container, it's just going to be moving downwards and it'll accelerate due to gravity there. If you had a real world situation like maybe a 2-liter pop bottle and you poked a hole in it, it would turn into a kind of calculus type situation if you wanted to push it there, because the leak would actually be enough volume flow rate to significantly decrease the top here. So you'd have a velocity term, but you would also have decreasing height. So over time, as this height decreases, this height here decreases, and you would see the initial velocity decrease as there's less water, lower pressure up here, and the leak would gradually move closer. So this equation also explains why that happens. Let's say we made it a little more complicated, and in addition to this, you did your projectile stuff, but let's say we can make life easier and bury it underground, but let's say now we have like a hole or a beaker or a cup that we're trying to fill with this water. We're going to go back to the assumptions we had before. So assume that the water level is constant up here. So H is constant. Assume that the velocity here is so slow, we can ignore that term. Maybe they're going to want to ask, how quickly does this beaker down here fill up with water? So we know the velocity. We calculated, or you calculated using projectiles, where to put this beaker so that it'll fill up. But how quickly, if everything stays the same as it is in this moment, how quickly does that beaker fill up? To do that, we need to use something called volume flow rate, which just tells you what volume is flowing out of the hole per second. It's a pretty easy calculation, but if you don't know how to calculate it, you kind of can't really do anything. So you can even assume we had like a given volume of this beaker. Maybe they told us it's exactly a liter or something like that. But if you want to know the volume flow rate, we know the velocity. That just tells us how fast it's going, but that doesn't tell you how much water is going every second. You have to use this equation for volume flow rate. So volume flow rate can be calculated if you've got water going through an opening by multiplying the cross-sectional area of the opening times the velocity. Let's take a look at the units real quick. Your area is going to have units of square meters. Your velocity is going to have units of meters per second. And then when you multiply those together, you're going to get units of meters cubed per second, which is a volume flow rate. So if you had a volume in cubic meters, maybe they'll give it to you in liters or milliliters or something. You could convert it to cubic meters, and then a volume flow rate in cubic meters per second. You could combine those two pieces of information to give you a time. This equation for volume flow rate is not directly listed on the AP equation sheet. It's listed in the form of an equation called the equation of continuity, which looks like this: A1V1 equals A2V2. This equation is used anytime you have a pipe that has a fluid going through it, and that pipe suddenly widens out or narrows, and it's going to tell you how the speed is going to change in those different parts. It says when you have a small cross-sectional area, you've got a high velocity, and then when you have a large cross-sectional area, you have a low velocity. And this equation will tell you exactly how those are related. And because A1V1, an area, cross-sectional area times the velocity, because that gives you a volume flow rate, the equation of continuity is basically implying that the volume flow rate is constant. So if you look at any place along this pipe, we're going to assume that the amount of liquid passing each of these points is constant. So for that to be true, then you would have to say that it slows down if you have a bigger area. This is also true in streams. So if you look at rivers and streams as they widen or as they narrow, when a stream narrows, you are decreasing the cross-sectional area, which means it goes faster. If you've ever been canoeing or kayaking, you'll probably notice that. When you get to the narrows, that's where your rapids, well, I don't know if you're kayaking through rapids, that's pretty extreme, but that's where it goes faster because of the equation of continuity. In a river, you've got a constant volume flow rate. There's nowhere else for the water to go. All the water is flowing through the river. So by combining this volume flow rate, cross-sectional area times the velocity, you could figure out how long it would take the beaker to fill. The last little piece of information you would need to do that is here is your cross-sectional area, the actual hole where the water is leaking out. So they would give you, or you would measure either a diameter or a radius, or maybe just the area directly. But they would have to give you some piece of information that would let you calculate that area. All right, these tricks are going to help you. So this derivation is one that you're going to have to know how to do if you see problems that have fluid leaking out of a container. I wouldn't recommend just trying to memorize this. That's not a great strategy. Know how to do these assumptions, know how to derive this equation in case you do. Then all you got to do is plug in your variables. And then anytime you're dealing with a volume flow rate, if they give you a velocity and they want to know how quick it'll take to fill up a container or anything along those lines, like the beverage problem you're going to see this week, remember, volume flow rate is just cross-sectional area times velocity. This should get you a great head start as you start working on the problems this week. But if you have any questions, please don't hesitate to let me know. I'd be happy to help you out.